All right, so we're continuing in our discussion about research methods. In the previous video, we talked about there being three general research methods: observational strategies, correlational strategies, and experimental strategies. In this particular section, we're going to talk about correlation. Now, if I were to ask you to define the concept of a correlation, you would say the relative strength of association between two or more variables, or how closely two phenomena vary together. Now, when we talk about correlation, I said that one of the nice things that a correlation can do for you is it'll allow you to predict behavior, right? So observational strategies allow you to describe behavior, but now we can predict behavior. In principle, if you had a perfect correlation, you could predict with 100% accuracy. But in reality, it's very rare to have a perfect correlation. And because we don't have a perfect correlation, we also don't have the ability to predict perfectly, right? So it's important to understand the stronger the correlation, the better or more able you are to predict. The weaker the correlation, the more imperfect the correlation or prediction becomes. Now, we also want to understand the concept of correlation coefficient. Now, that is the value that is going to be spit out when you run the statistical test, right? When you run a correlation, it will tell you exactly the strength of the association. Now, what's important to note when you get that correlation coefficient is there are two elements to pay attention to. There's the sign, and the sign can be either positive or negative. And then there's the correlation number as well, which goes from 0 to 1. So the closer you get to 1.00, the stronger the association is. So let's talk about it, right? So when we talk about a positive correlation, that means both factors go in the same direction. So either both factors are going to increase together or both factors are going to decrease together, right? So, for example, smoking and cancer. As smoking rates increase, or the amount a person smokes, the risk of developing lung cancer also increases, right? So both go in the same direction. And similarly, the opposite is true. As smoking decreases, the risk of cancer also decreases. So you see that they're both going in the same direction. Okay. A negative correlation is that the factors are going in opposite directions. So as factor A increases, factor B is going to decrease. So we refer to this as an inverse relationship or an indirect relationship. So an example would be increase exercise on average will decrease weight. Now, obviously, those people who engage in weight training and bodybuilding, they might argue, hey, wait a minute, my goal is to bulk up. But on average, people are not bodybuilders. So more often than not, the more you exercise, the lower your weight's going to be. It's going to help you lose weight. Or another example might be the relationship between gas prices and the amount you drive, right? So if gas prices are through the roof, you're going to want to drive as little as possible because it's going to cost you more money. So as gas prices go up, driving goes down. So this is a negative correlation. Now, there is a possibility that the two factors are unrelated, such as height and intelligence, right? So your height has nothing to do with intelligence. One is a physical attribute, one is a cognitive attribute. So we wouldn't expect as height to increase it to have any meaningful impact on intelligence. So when you take research methods, you might hear no correlation described as follows: as factor A increases, factor B both increases and decreases in a non-systematic way. Basically, there's no link between the two. Now, the sign, as you can tell, shows direction. Both factors go in the same direction with a positive correlation. With a negative correlation, the factors go in opposite directions. But it's important to note that the sign doesn't tell you the strength of the relationship or the magnitude of the relationship. It just tells you the direction. The decimal point itself will tell you the relative strength. So I'm going to put a couple things in the chat, and I'm going to ask you, which of these do you think is the strongest correlation? So give me a second. I'm writing the choices now, if you're wondering. Okay, so I gave you 4 choices. And the question is, what is the strongest correlation? Option A is positive 0.91. Option B is negative 0.93. Option C is 0.50. Option D is 0. So I'm seeing a bunch of A's. Now I'm seeing a bunch of B's, a couple C's. Does anyone who picked A want to explain their rationale for positive 0.91? Jenna?
I picked that one because when we were going over like no correlation, like oh wait. Oh wait, never mind. Oh sorry. I picked the wrong one.
Okay. So at the moment you want to change your answer to what? Jenna, what would you change your answer to? Did I lose you?
Oh no, sorry, I was just looking back at the choices.
Yeah.
I would say B.
Tell me why. Now, B, again, to repeat the choices, it's positive 0.91, negative 0.93, positive 0.50, and then 0.00. Okay.
Um,
So you're picking B as negative 0.93. Why is that?
because as you look at the example, like for no correlation, it says negative 0.91 is a strong correlation than positive 0.98. And I feel like as you go higher, I feel like it has a more stronger like correlation than the other choices. So I feel like to me it would make more sense.
So, correct. The reason why negative 0.93 is the strongest correlation is in order to determine the magnitude, you have to ignore the sign. As you recall, the sign is only telling you the direction. So if we eliminate the sign, which decimal point is the highest? 0.93, right? So that's the first principle that is important here is in order to determine the strength, you have to ignore the sign. The sign is only telling you direction. So let me put out another demo in the chat, and then I'll read it because people may not be in class, so they may want to know what the choices were. Give me 1 second. All right. So don't jump to answer. Take a look at this one. So I'm giving you 4 responses: negative 1.01, negative 0.99, positive 0.98, and positive 1.00. What is the strongest correlation? I'll let a bunch of answers come in. Okay. All right. I see a bunch of answers came in. So let's break it down. Now, this one had a trick in it, and a lot of you fell prey to it, right? So those of you who picked A, why did you pick A, James?
Because with the decimal on the, like it's 0.1, I mean 1 point, so it's higher, and unlike the positive 1.00, if that had a 1 in it, so that would be make it higher, no?
So you're saying ignore the sign, and
Yeah,
1.01 is the greatest number, right? So if you have
yeah.
$1.01, that's better than $1, right?
Mm-hmm.
But this is a checkout of knowledge. Believe it or not, option A is incorrect. So you're like,
Mm.
hey, wait a minute. How could that be? You might have noticed earlier in the lesson, I said from 0 to 1. If you ever see a correlation above 1.0, it's an impossibility. That is a typographical error. So obviously, this is a teachable moment that there can't, option A is a trap. It's not real. It's an impossibility. So if we were to ignore option A because a correlation can only go from 0 to 1, what do you think is the better of the choices? Negative 0.99, positive 0.98, positive 1.00.
It would be B then.
Say it again, James.
It'll be negative 0.99,
No,
right?
it's
It's
actually
not?
B. Remember, it can be a perfect correlation. A perfect correlation would be 1.00. And if you have
Oh,
99 cent versus $1, $1 is more than 99 cent. So what that was trying to do is teach you the second principle. So the first principle was the sign tells you the direction. So if you're looking at the strength of the association, you have to ignore the sign. The second principle is that a correlation can't be more than 1.00. So in this case, we do have positive 1.00, which would make positive 1.00 the correct answer. Interesting, huh? And I'm going to give you a third demo. Give me 1 second to write these out. Why is it not writing? Okay. Point. Okay. So listen carefully. The options are positive 1.00, negative 0.99, positive 0.98, and negative 1.00. In this scenario, what is the strongest correlation? Excellent. All right. So I see some, usually when I do this in class, I have people raise their hand for A, B, C, D, but some of you got the memo. So this again is a trap. If I told you ignore the sign, options A and D are the same, aren't they? Right? So who cares whether it's positive 1.0 or negative 1.0? Those of you who picked A are demonstrating a bias, right? We have a natural bias towards positive numbers. But in reality, if you had a positive correlation of 1.00 or a negative correlation of 1.00, they're of equal strength. Remember, strength and magnitude is about the number, not the sign. So I saw, who was the first person who said A and D? Will, way to go. Right. So obviously on a test, I wouldn't do that to you. You have to have one correct answer. But what I love about these three demos is it shows natural biases, right? So the first lesson was to ignore the sign when it comes to correlation. The second lesson was that a correlation cannot go above 1.00. And the third lesson is when you have two correlations of equal value, once again, do not default to the bias of positive numbers. So I hope those three demos were fun. I hope that those demos crystallize the concept. So let's continue. Now, a perfect correlation. Now, a perfect correlation is a correlation that you can connect all the dots in a scatter plot with a single straight line. Now, a perfect correlation of positive 1.00, you'll see that it's sloped upward to the right, but you can connect all the dots with a single straight line. A perfect negative correlation, you can see you can also connect all the dots with a single straight line. However, it's sloped downward to the right. So visually, you'll know what kind of correlation you have by the trend of the dots. If it's sloped upward to the right, you're looking at a positive correlation. If it's sloped downward to the right, you're looking at a negative correlation. Now, I said to you, it is very rare that you have a perfect correlation. So the idea of connecting all the dots with a single straight line is not likely. Now, you'll see I skipped the concept of no relationship or no correlation, right? So when you look at no correlation, do you see how the dots are all over the place? Can you give me a line that would reflect the trend of these dots? Is it going upward to the right? Is it going downward to the right? The answer is neither, right? So when we do no correlation, it is most common to depict no correlation as a flat line going across the middle. So think about it as having no pulse, right? So when you have no pulse, it flat lines, right? So no correlation is a flat line. Now, some statisticians don't like the idea of doing a flat line because that's arbitrary. And instead of the flat line, they do a circle around all the dots. And a circle, the beautiful thing about doing a circle is there's an infinite number of single straight lines that you could draw so that you get out of, oh, why did you draw a flat line horizontally, right? So these are the concepts of perfect correlation. Now, I introduced to you other terms as well, right? So I introduced to you the term of scatter plot. A scatter plot is a visual representation of the dots. Now, keep in mind, with a correlation, you're linking at a minimum two variables. So each dot on the graph is a value of factor A and factor B. Now, the dots as a whole for all of the participant is what we call the scatter plot. Now, I said to you, in general, there is typically a trend. Are the dots sloping upward or downward to the right? If it's sloping upward to the right, we have a positive correlation. If it's sloping downward to the right, we have a negative correlation. Now, what we tend to do is draw a line through the middle of the dots to depict the relative direction it's going in. Now, the closer the dots are to the midline or the line of best fit, the stronger the association is. As you saw with a perfect correlation, the line, all of the dots are on the single straight line. But the reality is, as the dots spread away from that line, you have a weaker and weaker correlation, right? So you have more and more error in your data set. You couldn't predict as accurately when you have a wider spread of dots, right? So does that make sense? Any questions on the concept of correlation, positive, negative, no relationship? Any questions on the concept of the graph and the scatter plot as a whole, and the line of best fit, which gives you it's a trend line, gives you the general direction of the relationship. Jenna.
Do you
Jenna.
think you could repeat that again about when you were saying like how it meets in the middle when you connect them and it has like a stronger correlation?
So if you have, let's imagine you have 100 participants, right? And actually, I'll go backwards to depict this, right? So this is a perfect correlation. You see my cursor going upward on the green dots,
Yeah.
right? So a perfect correlation, you would draw the line of best fit and you would be able to connect all the dots with a single straight line. But by the way, this is called a scatter plot with all of the dots in general. But let's say we didn't have a perfect correlation. We might have, oh, can you see my cursor? We might have a dot here. 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 Do you see my cursor moving around?
Yeah.
So
Yeah.
the fact that I have data points off of the midline, well, that's going to show a variation from a perfect correlation. The wider the spread of the dots, the weaker the correlation. Now, this is a good example of the dots are so spread out, it eliminates the relationship altogether, right? Now, we wouldn't want this, right? This is bad. But let's say if you look at my cursor, let's say I had a dot here, a dot here, a dot here, a dot here. There is a clear trend of the dots. It's just not a perfect correlation. The wider the spread, the weaker the correlation becomes. Does that make sense?
Yeah. Thank you.
You got it. All right. Now, we talked about that. I also want to talk about some potential errors. Now, when we look at extreme scores, so if we were looking at a scatter plot, we might have outliers or dots that are so far off the line of best fit or the midline that it doesn't make sense with the rest of the data. And sometimes when you have an outlier, there is a natural tendency when you retest for it to regress towards the mean. I'll give you an example. If you have an extremely high weight and you do small changes, if you retest a person's weight 3 months later, even with small changes, there is a natural tendency to revert closer towards the weight one is supposed to be, right? So biologically, we have something called a biological set point. Our body has an understanding of the weight it's supposed to be. And the farther we are away from that, if we make small changes, it's possible to revert backwards. Does that make sense? So the more extreme the score, the more likely is on retest, you're going to revert towards the average or the midline. So that's the problem with outliers and extreme scores. Now, there was a show that capitalized on this concept called The Biggest Loser. Anyone ever watch that weight loss show?
Yes.
Right.
Yes.
Excellent. So if you've watched it, what they do, which is fraudulent, is they take people who are morbidly obese and then they put them through an exercise routine, dietary changes, and they're like, oh, look how much they're losing. Well, it's good for drama, it's good for television, but in reality, that same routine wouldn't work as well if a person was not morbidly obese. And similarly, minor changes would have lowered their weight even outside of that routine. So the series made a lot of money off of this. They wrote exercise routines, cookbooks, all kinds of things to capitalize on people of extremely high weight. But you'll notice at a certain point in the season, people start to hit a wall. And why is it that they hit a wall? It's because regression towards the mean, once you get closer to your expected weight, you need to do more to get to where you're supposed to be. That diet and exercise routine isn't in of itself enough, right? So you have to have time, you have to have calorie deficit. There are a lot of other things that come into play. But at an extreme weight, sure, you're going to have regression towards the mean. I see there's something in the chat. Okay, there was just a response, yes. All right. So the other thing that I want you to understand about correlation. So we talked about correlation as having the ability to predict an outcome. But correlation and causation are not the same thing. Just because two factors are related doesn't mean factor A necessarily caused factor B. And I'll give you an example. There is a strong positive correlation between self-esteem or low self-esteem and depression. So is it possible for low self-esteem to lead to depression? Sure. But is it possible that it was depression that led to low self-esteem? Sure. So in science, we call this the chicken or the egg phenomenon. Which one came first? And with a correlation, we don't know. In some cases, maybe it was the low self-esteem that led to the depression. In other cases, maybe it was the depression that led to low self-esteem. So if we don't have a clear understanding of which came first, we can't refer to it as a cause. Now, another problem we have with correlation is there are confounds, or what we call the third variable problem. There are infinite number of outside factors that could actually cause both A and B. For example, if I were to say a person experienced a trauma, right? So a traumatic event, could that be a factor that leads to both low self-esteem and depression? The answer is yes, right? So because we don't know which one came first, and because there are other factors that could have caused both, we can't refer to causation with a correlation. So that's one of the limitations. Correlation, we could predict an outcome, but we cannot determine cause and effect. And in some cases, it's even illogical to assume that factor A is causing factor B. I'll give you an example. There is a well-established correlation between ice cream sales and murder, right? So, is it people eating ice cream that is causing murder? No, that would be ridiculous, right? There might be an outside factor that is related to both of them. Can anyone think of what might be driving both ice cream sales and murder? Anyone?
Would it be like targeting like against little kids? Because maybe like kidnappings.
No,
No,
no. This is more broad than that. So the idea of, when do we have our largest ice cream sales?
summer.
In the summer, usually, right? Because it's hotter. And when do we have our highest rates of murder? In the
With a
summer,
lot of crowds of people.
right? So in the summer. So there's something about the summer that is causing both. And there are actually several things that might be at play. Number one, there is a connection between heat or temperature and aggression. So as it gets hotter, aggression rates go up. In fact, this has been demonstrated even in Major League Baseball. When you have a pitcher on the mound, more batters get hit by pitch as the temperature goes up. So there is a link between temperature and aggression, right? So that's one thing. So that might explain the ice cream sales and all of this going on. Another thing about the summer is that the day is longer, and we see that people have more free time. And these factors also are linked to aggression, right? So if you were working in EMS, you were doing shift A, B, or C, you would see that the morning and the afternoon shifts, there's a lot more happening than the overnight shift, right? So again, there are a lot of factors here. So going back to the idea of there being a positive correlation between ice cream sales and murder rates, that correlation is meaningless, isn't it? Right? So it's not saying that the ice cream sales caused this. There are outside factors. Remember the third variable problem. There are a whole host of other factors that are explaining this relationship. So I hope that example does justice to the third variable problem, and how we cannot say there, just because there's a correlation, that there's a causal relationship. One more thing. Remember Sir Francis Bacon, and he talked about how we make cognitive errors. Well, one of the cognitive errors we make is what's called an illusory correlation, right? Where we perceive a relationship when none really exists, right? So we attribute patterns to random events. So if we were to flip a coin, and we were to flip a coin 6 times, you could get a head or a tail, right? H is head, T is tail. And we had these 3 options. So the option A is 3 heads followed by 3 tails. Option B is a head, a tail, a tail, a head, a tail, a head. Or option C is 6 tails in a row. Which of the patterns is most likely? Now, if I didn't give you the answer on the bottom, most people would pick option B, right? Because you might say to yourself, what are the odds of getting 6 tails in a row? Or you might say, what are the odds of getting 3 heads followed by 3 tails? And you might create the belief that the odds are different. But in reality, in mathematics, the odds of all 3 of these are equally likely, right? Think about from a probability perspective. What is the formula for probability? Observed outcomes divided by total possible outcomes. So every time you flip a coin, you have a 50-50 chance, right? A 50-50 chance of a head, 50-50 chance of a tails, right? So even though it looks like one is more likely to occur than another, if you flipped a coin 1,000 times, which is when we talked about sample size, a sample of 1,000 is large enough to be representative. Without fail, you have all 3 of these patterns emerge. And if you flip a coin 1,000 times, you will also see that there's roughly a 50% frequency of a head and a 50% frequency of a tail. And I say roughly because, every experiment's going to have some margin of error. But it's interesting, right? So because we only flipped it 6 times, it looks like, oh, come on, option A, that wouldn't happen, or certainly option C wouldn't happen, but all 3 of these would happen, and the probability of all 3 are equally likely, right? So from a mathematics point of view, people who select one series of outcomes over the other, it's an illusion. I'll give you another 2 examples of illusory correlation or looking for patterns in random events. If you follow sports, there is this idea of a hot hand or the hot hand effect. So the person who's making the shot, feed them the ball, right? So with that, the assumption is if you made a shot, you're going to make the next one, right? Now, check this out. Let's take a player like Shaquille O'Neal. Shaquille O'Neal was known for being a really poor free throw shooter. But let's say one night, this is what happens. He gets fouled, and he makes the first free throw shot. And then he makes a second free throw shot. He gets fouled again. He makes a third free throw shot in a row. And then a fourth free throw shot in a row. He gets fouled a third time, and then he makes a 5th free throw shot, and then a 6th free throw shot in a row. So now he has made 6 free throws in a row. He gets fouled again, 7th time at the line. Is he going to make it, or is he going to miss it? What would you say?
He's gonna make it.
He's going to make it, right? Joseph? He's going to make it. Anyone say he's going to miss it?
I was gonna say it's like 50-50.
Okay. Hold on to
could-
that for a second.
Okay.
How many of you would say, oh, he's made 6 in a row? Remember regression towards the mean, he's bound to miss this next one. The reality is that Joseph is correct. Every free throw shot is its own singular event. When you use the previous 6 shots to predict an outcome on the 7th, it's an illusion. So those of you who said, oh, he made 6 in a row, he's on a streak. Well, that is, you could use that argument to say the streak is going to continue, or you could use the argument based on regression towards the mean that that streak is going to end. But in reality, if we extract that one free throw shot from everything else, remember the mathematics of probability. Number of observed outcomes divided by number of total outcomes. There is a 1 out of 2 chance that he's going to make it and he's going to miss it, because it can only be one or the other, right? So the actual observed outcome is 1. The possible outcomes is 2. So when we do it, it's a 50-50 shot. But people will use this as an argument to say, okay, well, he's going to make it or miss it. Now, follow Shaquille O'Neal across the season, and his free throw percentage will be roughly what it is on the back of his sporting card for each season. So that seemingly, or that short interval that looked like a pattern, looked like a streak, will disappear across a larger sample. So just because you're caught in the moment doesn't actually mean that mathematically this is true. So the hot hand effect mathematically is a debate, and we argue against it actually from a mathematics point of view. Same thing can be said when people go to the casino. Oh, this table is hot. Oh, this table is cold. The idea of having a hot table or a cold table is similar to this illusory correlation or attributing order to random events. If you sit at a blackjack table, let's say, long enough, you are going to lose your money. Because even if you know blackjack and you follow what's called basic strategy, the house, the casino, still has a 0.5% edge over you. So you play long enough, you're going to lose your money. So, oh, this table is hot. Oh, this table is cold. No, the table is the table. The cards are the cards. There's no emotion in the cards. There's no decision-making process in the cards. All you can decide is whether you want to stay or go. But mathematically, you flip those cards over enough times and you will lose money. And that's why the lights stay on in Vegas. All right? Any reactions to correlation? Because I think that's a good place to stop the recording. And then we'll talk about experiments in a separate video.